Hi everyone, my name is Yichen Huang and I'm here to present our work, the Mixed Burst Dispersed Moran Process, which is going to appear at ITCS 2026. This is joint work with David A. Brewster, Michael Mizemacher, and Martin A. Nowak, and we're all from Harvard University. What is a Moran process? It aims to describe evolution in structured population, and it's modeled as a graph. Each vertex, you can think of that as a location, and one location is going to hold one individual. There are two types of individuals. There are residents with a normalized fitness of 1, and there are mutants with a fitness of R. This R could be larger or smaller than 1. If R is larger, that means this mutant is a strong mutant, or if R is smaller than 1, this means the mutant is a weak mutant. We don't care about the exact identity of the individual, but more its type. At each time step, the evolution is going to evolve according to some update rule. Previously, the most studied update rule are birth death update and death birth update. In birth death update, each discrete time, we first pick a reproducer U proportional to fitness. So if your fitness is larger than 1, you are more likely to get selected. After that, we will pick a random neighbor uniformly at random, and then the reproducer will place a copy of itself onto that neighbor. In death birth process, we first pick a vertex uniformly at random to die, regardless of your fitness. Then, among all your neighbors, they are going to compete for this new vacancy according to their fitness. So if you have larger fitness, you're more likely to gain the vacancy once someone dies out in your neighbor. And then you place a copy of yourself into that location. So it is worth noting that selection only appears on the birth. So if you have higher fitness, it's more likely that you will give birth at some time. But death is uniform regardless of your fitness. It's plausible that you can study, okay, what happens when selection also happens on death. I think biologists have some reason that why they would like to select to describe and study this selection on birth type. I mean, these two are also the most studied ones, so here we focus on these two. But in principle, you can study other cases. And this is also why the B is capitalized for birth and D is not capitalized for death. Okay, and then this process is going to continue until only one type exists. So if the final graph only consists of mutants, we call that fixation. And if the final graph only consists of residents, we call that extinction. And when either extinction or fixation happens, we say that this evolution process absorbs, meaning that, okay, this round of evolution is finishes. Okay, and usually what do we care about? We care about fixation probability, which is that I give you a initial location of the mutants, and I want to know, okay, what is the probability that the mutants takes over and replace all the residents? And we also care about, okay, what if, I mean, at some configuration, what is the expected time step until an absorption happens when there are only mutants or residents? Now, you might note that the fixation probability is parameterized by the starting location, and sometimes we don't do that. This is because usually we care about exact values of fixation probability, well, because it's a real number between 0 and 1. Well, for absorption time, we usually care a little bit more about the asymptotic values, like say, oh, is it a polynomial or exponential in terms of with respect to the size of the graph. And usually we cannot actually solve for the exact value for fixation probability unless in very specific regimes. So we usually want some approximation schemes for it. And therefore, the natural way of doing that is to try to do Monte Carlo. So you just play and experiment and simulate this evolution for many, many times and record how many times fixation happens. And okay, you say this is a good approximation. And we have like standard Chernoff bounds to show that it's very close. But in order for it to be a FPRAS, a fully polynomial random approximation scheme, we usually want that we need that the fixation probability is lower bounded by 1 over a polynomial in the size of the graph, because the number of experiments you need is inversely related to the absolute value. And we also need the absorption time to be polynomial with respect to the size of the graph, because otherwise just simulating could take too long. So if we have these two polynomial bounds, we have a fully polynomial sampling scheme, and that's going to be the goal of a lot of results that we'll describe later. Okay, So what do we already know? Well, we know a lot of things for the pure burst test and death burst update. So for each of these pure update rule, we know polynomial absorption time. We also know fixation probability, uh, like roughly what they are, and okay, what graph will make it evolve fast, what graph make it evolve slow, what graph increase the fixation probability, what graph decrease the fixation probability. But all of these results are rule dependent. And in particular, there are some results that are contradicting or has high discrepancy between the rules. So there are some graph that burst as update rule is going to absorb very quickly on this graph, but on this verse it's absorbed much slower. There are graphs which is amplifier, which has high fixation probability for burst test, but has low fixation probability for death burst. So it's kind of unfortunate because it makes it hard to compare biological stories and interpretation, and we don't know, okay, what is really general feature and property across update rules, or what is just the artifact of a specific rule. So in this work, we try to study interpolation between two pure update rules and hope to give some understanding to the unified model. So this is a very simple idea. Instead of saying, okay, I am doing burst test update or I am doing death burst update all the time, I say each discrete step, we do a burst test update with probability lambda and we do a death burst update with probability 1 minus lambda. Then hopefully this captures some uncertainty and variation in the updating mechanism because, well, in real life, right, in real scenarios, we cannot say that it's update exactly like this. It has some amount of uncertainty or randomness happening. So this is in some sense more realistic, and you can switch the regimes of lambda to study like different kind of update. And also it lets us ask like which phenomena, which properties are robust across update rules. As I just said, it's not very ad hoc and specific to some update rule, but okay, it may work. Or I mean, we can also ask like phase transitions for some properties in terms of lambda and understand, okay, which phenomena are general, which phenomena are specific, what are the regimes that these phenomena is going to appear. Okay, so let me begin by showing you some interesting results. So a natural starting point is to think about lambda equals 1/2, which says, okay, a burst test and death burst update happens with equal probability. And then the first result we know is that if lambda equals 1/2 and r equals 1, which is neutral update, is usually also the starting point of any update rule that you want to study, then for any initial mutant, your fixation probability is exactly 1 over n. Okay, so regardless of how your graph look like or where do you start, your mutant is going to fixate and takes over the whole graph with probability 1 over n. So this is drastically different from only burst test or pure death burst. So it is known that if you do burst test update, the fixation probability is proportional to the inverse of the degree of your initial location. And if you do death burst, it's proportional to the degree. And then if you have like an initial set instead of a single mutant, when r equals 1, this is additive. The fixation probability is just a sum of the fixation probability at individual locations. This only appears for r equals 1. As I said before, in general, we don't know how to solve fixation probabilities exactly, unless you solve a linear system of exponentially many variables. For r equals 1, we know it. Okay, and it might make you tempting to think that, oh, like for burst test, it's proportional to 1 over the degree. For death burst, proportional to the degree. And when lambda equals 1/2 is proportional to constant. So maybe it is proportional to the degree to the 1 minus 2 lambda. Okay, this is not true. I mean, I thought about that a little bit, but it's not true. So what's interesting here already is that, well, at the beginning, we want to understand that, well, is the fixation probability that the value of which the exact value that we care about, is it monotone with respect to lambda, right? If it is monotone, then it's pretty good, and it's actually not clear. Yeah, you kind of expect it to be monotone. There's also reason you expect it to be not, and turns out it's not monotone. Even just looking at these three points, the two endpoints and the middle point. So look at this specific graph with 5 vertices and the 6 edges. And you do the calculation, you figure out that the fixation probability at lambda equals 1/2 is larger than both endpoints. Okay, and therefore this is not monotone anymore. And this already kind of gives some evidence that this lambda mixed process is an interesting thing on its own. It's not just some combination of the two endpoints. Okay, and how do I prove that the fixation probability is exactly 1 over n? It's actually a martingale technique. I will give like this as an example because most of our proofs involves a kind of a similar idea. So we consider a potential function, phi of s, where we use s to denote the, so s of t is the set which the mutants occupy at time t. It's a random variable. And then we say, okay, we will look at the expectation of phi of st plus 1 condition on st. So how do we do that? Well, we consider every boundary edge uv. By boundary edge, I mean u is in S and v is not in S. So the boundary at which one endpoint is a mutant, the other endpoint is a resident. Now, what is the edgewise drift? So what is the edgewise drift? I mean the contribution of increasing the potential by u replacing v minus the contribution of decreasing the potential when the resident v replaces u. So what happens when we specifically require that what is the contribution of this specific edge? Okay, and well, if you calculate that, you figure out that the effect of birth death and death birth is going to cancel out with each other. So what do I exactly mean here? So this 1 over n is the probability that u gets selected for birth, and with probability 1 over degree u, it selects v to replace. And then this is when we're doing birth death. And then there's 1 over n probability that v gets selected, and with probability 1 over degree v, v replaces u. This is doing death birth. We have 1 over n probability that v gets selected for death. With probability 1 over degree v, u replaces v. So this is when we get an increase. And vice versa, this is when u gets selected for death and v selected for birth. And we know that the edgewise drift is 0. So if you sum over all the boundary edge, this is the expected change in the potential, and this is 0. Therefore, we know that phi of s is a martingale, right? So we know that absorption happens when phi of s is n or 0, and you start with phi of s is 1. Because it is a martingale, the probability that you reach phi of s is n is exactly 1 over n. So this completes the proof. And we also have that the absorption time as a function of r is n to the 4. Well, like this is as a function of r, it's not some crazy function. When r is larger than 1, this is r over r minus 1. When r is smaller than 1, this is like 1 over 1 minus r or something. It's not like a crazy constant with respect to r. And then this implication, as I said before, because like, right, when r is larger than 1, we have a fixation probability that is bounded by polynomial, and we also have polynomial fixed absorption time, so we can do Monte Carlo and we'll get a f plus for fixation probability for general r. Yeah. Okay, so how do I prove the absorption time? Well, if r is not 1, well, we assume that r is larger than 1, otherwise you can pretend r is 1 over r and replace the role of mutants and residents. Then again, we use phi of s equals s, and then we have a uniform positive drift away from the absorption. So where does that come from? Well, if you look at this equation, now for all the positive term, when the mutants replace the residents, instead of 1, this becomes a r. So you get a r minus 1 divided by like roughly n cubed. Therefore, this is like the expected increase in your potential. So you cannot do that too many times by like some martingale arguments. Therefore, this gives us the absorption time. If r equals 1, this is a little bit more complicated because your potential change in expectation every time step is 0. But now you can use the quadratic potential and show that like you still get some increase in the potential, and in general this cannot take too long, and you have n to the 4. And I also want to note that this matches the best bound that we know for death burst update. For burst test, there's a much more involved algorithm. Arguments show that the absorption time is like roughly order of n to the 3 plus epsilon. I conjecture that it's also true for other cases, but it's very complicated and we don't do that now. Okay, so just now, the reason why we get very clean model is that when lambda equals 1/2, there are a lot of symmetry that cancels out a bunch of terms. There are another way that makes it very symmetric, which is when the graph is regular. So if with the graph is regular, then there is no degree bias, and then burst test and depth burst is like roughly the same. Okay, so it's very easy to show that when r equals 1 for every lambda, if your graph is regular, then the fixation probability from any starting point is 1 over n again, and then the fixation probability from any starting set is the size of the set divided by n. Also, you have n to the 4 absorption time. The proof is basically the same as before. As soon as you get the fact that you manage to find the potential such that it is a martingale when r equals 1, when in neutral revolution, then you should be able to make everything work. Okay, now regular graph is a very strong requirement, right? So I'm hoping that, okay, maybe we can get away from the strong regularity constraint. And if the graph is not too far away from regular, like the degrees are close to each other, then it might still be able to, we might still be able to control that, right? Like the bad case is when in this graph, the degrees are not equal. And then this 1/2 doesn't cancel out. It becomes lambda and 1 minus lambda. And then we don't know if it is positive or negative. We want to have a single-sided edgewise drift in order to get like controlled behavior. But okay, what can we expect? Well, if your R is very large, right? If your R is so while in some cases your degree is this value, you don't know if it's positive or negative. We actually have a coefficient of r here in this first term, in these positive terms. So if your r is large enough to offset the fact that your denominator is different, we can probably get all the way positive drift, and therefore we have the bound that we can get. So this is roughly the idea of what we prove. Okay, and we show that if the ratio between the maximum degree and the minimum degree in the graph is alpha, and that r is larger than alpha squared, then we have polynomial absorption time and 1 over polynomial fixation probability using the martingale technique and the idea that I have said before, that we get single-sided edgewise drift. Now, why do we care about why do I care about almost regular graph? Because almost regular graph is actually very, very common. If you think of a Erdős-Rényi graph with a GMP and the P is not too small, then your degrees is going to concentrate around a -1 over P. Sorry, a -1 divided times P. And then G is like alpha almost regular with very high probability for if you think of alpha as a constant, right? And then therefore, with high probability over random graphs, we have the previous results that this lambda mixed Moran process, for any lambda, we have polynomial lower bound and for fixation probability and polynomial upper bound for absorption time. And then we get a f-ras for the fixation probability, which is the value that we care about. And in particular, we can say if you take p equals 1/2, then the probability of alpha almost regular graph becomes the ratio, like the proportion of almost regular graph among all the graphs. And this result can be in turn understood as, well, for almost all graph, for 1 minus small o of 1 portion of all the graphs, there is a good sampling scheme for it. Okay, so just now we have said that if you're regular, then things are very good. And then if you're close to regular, it's also very good. And we say close to regular in the sense that the degrees are within like a relatively small range. There is another way of being close to regular, which is that, okay, the types of degrees are very limited. So either you have a very large degree or you have a very small degree. Maybe like, say, for example, you think of a star or like a double star, something like that. Okay, so this is when we discuss bi-degree graph. So the degrees only take two values, d1 and d2, and it include many famous graph families. So we have star, we have path, we have biregular graphs, we have friendship graph, we have wheel and book. So all of these. Okay, and then we have some exact fixation probability when r equals 1 that I can solve regardless of lambda. And this is like a little bit involved thing. But how do I get this equation? What I really do is just um, when there are only two possible values of the degree, I can explicitly solve for the potential function that make the edgewise drift equals 0 when r equals 1. And using that, you can solve a lot of things. And similarly, you use the potential that help us derive this equation, we can show that the absorption time is also uh, not very large. Therefore, we again get a f plus when r is at least 1. And now note now that I don't need to assume r is larger than alpha squared. I only need that r is larger than 1. So in general, like also in previous works that you cannot do anything when r is smaller than 1 because then your fixation probability can be arbitrarily small and we don't have a meaningful bound for sampling it. But before we can do r is at least 1 for bursts and disperse, in this kind of graphs, we can also do that for any lambda. Okay, so let me quickly do a summary. We try to study this lambda mixed Moran process that is a principal bridge between the two well-studied Rolls bursts and death bursts. And then we have non-monotonicity in the fixation probability in terms of lambda. And then we have a few results for lambda being 1/2. We have regular graph and we have almost regular and random graphs and or by degree graph. Across these regimes, we have polynomial bounds, upper and lower bounds for fixation probability and absorption time. So I admit that these results are probably not very surprising. We do expect that they have these bounds as the two endpoints. But showing that demonstrates some robustness across different regimes, and we hope that this can stimulate further work. Okay, and I will conclude with a few open questions. So for pure BD results, as I mentioned before, there is a n to the 3 plus epsilon absorption time bound. For disperse, we don't even know that, so we probably also don't know that for the mixed process, but I think it would be interesting to study the tight bounds. Okay, and then you can also extend to directed and weighted graphs, and then this mixing is going to introduce a little bit more asymmetry, and it would be interesting to see what happens. We can also ask like some characterization results for this mixed process as well. So for pure burst test, there is some family of graph called isothermal graphs that has the fixation probability equal to the complete graph for any r, not just r equals 1. For disperse, I don't know if there are these isothermal graphs, and those kind of graphs exist for the mixed process. That's also interesting. And then we can also ask similarly a similar question that we have asked for bursts and disperse: which graph makes the fixation more likely or more unlikely? Which graph makes the absorption faster or slower? As a function of lambda or as a function of different regimes of lambda? These are all interesting questions. And thank you for your attention.